Welcome back. In this part of Lesson 8, we're going to do a quick review of limits from single variable calculus so that as we get into multivariable limits, the ideas are fresh in our head. Recall from Math 1A, single variable calculus, that the limit of a single variable function was equal to a constant L, and we write this in notation, the limit as x approaches a of function f of x equals L, if and only if we can force the distance between the output value of f of x and the limit L to be as small as we want by forcing x to be appropriately close to the input value a. This is a bunch of words. Let's take a look at a graphical representation of what we mean. Here I'm trying to give you some intuition with parentheses. There are ways to formalize this. If you've ever seen epsilon delta definition of a limit, this is what this particular overview looks at. But the concept of a limit as follows. Pretend you have this graph of a function f of x. Here we'll call this axis the input axis, and then here we'll call this axis the output axis. Probably in your calculus classes, if you did not do a formal, precise definition of a limit, what you saw was, a limit exists. So in this case, the function value doesn't exist at L, but if you go towards the value of a from the right, and you go towards the value of a from the left, you actually get to the same limiting value. However, really what's happening here is if you choose any distance away from L, maybe you do, this is what we call an epsilon ball. You don't have to worry about this. Basically just choose some distance on the top and the bottom of L, so some distance away. And the claim is, no matter what this distance is, even if this distance was like 10 to the negative 10 million, really small. If I can choose for any distance, no matter how small, some interval, if I can force some interval in the domain space such that as long as my x value is within that interval, so maybe I call this x, then I'm guaranteed that my f of x is within this distance. That's what a limit is. That's what we say about a limit, right? To say like, okay, we can get arbitrarily close, we can choose as many of these as we want to, and as long as for every possible one that we choose, we can always find some interval in which, for that interval, our x values always lie between L and that distance. That's what we say a limit is. So in words, you could just say, okay, the output values of f get really close to the limit L as x gets closer and closer to a. This is an overview of the ideas of a limit. Let's go ahead and talk about how we do this. So mathematically, we say to force the distance between our function f of x and limit L to be arbitrarily small, what we allow ourselves to do is say, well, the distance between real numbers, because remember, in single variable calculus, the output of a function is a real number. This distance is given by an absolute value, and we say we want to choose an arbitrary tolerance. So this thing right here, this is the Greek letter epsilon. Epsilon. And I like to write it like a small c, and then right under the small c is a larger c. So that's what that looks like. And it literally means tolerance. And the way to think about this is some arbitrarily small number. Right? So the concept is if I can choose any small number, no matter what it is, and I can always get this distance bounded by choosing x appropriately close to a, then I know that I can say, well, indeed, f of x goes to L. And one of the things to say, remember, the whole idea of getting f of x really, really close to L depends on letting the x value get really, really close to A. So what we say often when we're looking at that particular concept in limits is we say that for each epsilon there is some delta such that as long as x and A are no farther than delta apart, then f of x and L are no farther than epsilon apart. You don't have to worry about the formalities here. Just remember the whole concept is that input values drive output values. So if we look back at this diagram, here, if we're trying to get f of x within epsilon of L, within any arbitrary tolerance, in this diagram, we see that as long as x is within these two red lines right here, I'm going to be fine. But if I'm looking for a single interval, if I'm looking for like an A plus delta, and then around that an A minus delta, I might be a little bit more conservative. And I might define the interval to be the one that allows me to do that pretty well. And that's what's going on here. As long as I'm within some distance away from A, I'm going to be guaranteed to be within my arbitrarily small constant away from L. And that's when that limit exists. Please don't worry. This is not formal. I'm not going to test on this. This is just get you into the spirit of how limits function. So when we look at this, we say that x minus A is less than delta if and only if negative delta is less than x minus A is less than delta. And this comes from a kind of popular thing in inequalities. We say that if the absolute value of x is less than a positive constant c, then negative c less than x less than c. And this is actually an if and only if statement. You can go both directions on this, which is kind of cool. And then, of course, I can bring the constant a over to both sides by just adding, and this is exactly what we see here. The distance, as long as the distance between x and a is short within some delta, the claim of the limit is so too will the distance between f of x and L be within the arbitrary constant epsilon. So that's kind of a powerful realization here. In the case of single variable calculus, we said that the limiting behavior of the output of f of x had to be the same no matter what direction we approach our input value a in the domain. Because f of x is a single variable function in ordinary calculus, there are only two directions to consider. There's only two paths from which we can approach a. And you probably remember this. One path to approach a is when x is less than a, and we approach a from the left, so we really force a or x towards a this way. In this case, we say x is less than a and really close to a, and we kind of approach it this way to see what happens in the output. The other direction, because it's only a one-dimensional input, we say that x approaches a from the right-hand side, which means we're within some distance, and as we get closer and closer and closer to a, f of x hopefully will get closer and closer and closer to L. So here, x would be greater than a, and x approaches a. And that's how we kind of figure out what the limiting behavior was. We had a theorem that said that in order for this limit to exist, in order for the limit as x approaches a of f of x to equal L, the function output, the f of x value, must converge to the same value L no matter what direction we approach a. In other words, the left-hand limit is equal to L and the right-hand limit is equal to L. And we said that as long as this is true, then the limit exists. In Math 1C, we're going to introduce this as the concept that the limiting value must be path independent. No matter what path you travel in the domain, if the limit exists, we should always end up back at the same output value. The reason this is important is in multivariable limits, we're going to see there's more than one possible direction, or more than two possible directions. This observation right here, we're going to generalize as the two-path test. Just like if the left-hand limit is different from the right-hand limit in Math 1A, the limit doesn't exist. So too in Math 1C, if we can find two different paths that produce two different limiting values, we will say that the multivariable limit does not exist. In the next video, we're going to take a look at the concept of a multivariable limit by thinking about changes in distances. Then we're going to do a bunch of examples on how to take limits using multivariable functions. See you in the next video.